for him. That's good. So our today's speaker is our colleague Andreas Emil Feldmann from Karlsruhe University, and he will speak about parameterized algorithms for survivable network design.
Okay, yeah, thanks.
Thank you for coming.
Yeah, well, thanks for the invitation. Nice pizza. So, as said, my talk is, well, it's based on this very new paper with the title Parameterized Complexity of this problem called Survivable Network Design. So Survivable Network Design Problem. That's the usual acronym. Okay, there's something going on here.
Yes, autofocus somehow.
Okay.
It's not okay still. No. Let's try to start again.
Oh yeah. Okay, so since we start again, let me repeat the title. So parameterized complexity of survivable network design problem. And yeah, so this is work with some other people also, namely with Anish Mukherjee. See if I can write his name correctly. Okay. G like this, and Eikyan van Leuven. Okay. Now there's some good news because this paper was just accepted to a conference, and okay, that's good news for me. But there's also good news for you because the conference is SOSA, which is Symposium on Simple Algorithms. And that means that everything I say today will be simple. Okay, so that's yeah, so it's going to be SOSA 2022. Okay. Good. So I guess the first thing I should do is introduce the problem. So what is this SNDP problem? So it's if you know what the Steiner tree or Steiner forest problem is, it's a generalization of that. So it has some additional redundancy condition. And okay, so let me be more precise. So SNDP, you are given some graph, okay, vertices and edges. You are given a set of terminals, okay, so a special set of vertices, which we call R. These are the terminals. And the idea is you want to somehow connect these terminals in the cheapest possible way, okay? Cheap means that there is some weight function or cost function. Okay, here it's called cost. Maybe it's not so important what it's called, but okay. So there's this cost function from the edges, and okay, all the edges have like non-negative costs. All right, and then there are demands. So for how do I want to do this? Do I want to? I'll try to split this. Okay. For every pair of terminals, there is this demand dst, which is some integer. All right. Okay, that's what's given. All right, and the thing is, now you want to find some subgraph which connects the terminals according to the demands. So that means that yeah, and so essentially, if you look at two terminals S and T, so I draw terminals as boxes, okay, while the other vertices are like the usual dots, and essentially you want like this demand many disjoint paths between these two terminals. And depending on what kind of disjointness we're talking about, you get different variants of this problem. Okay, so it could be edge disjoint or vertex disjoint or something like that. Okay, so So I will just write, no, okay, so let me do it this way. Okay, so if for, let's see, for every pair of terminals, we have that the edge connectivity, right, which is usually denoted by lambda. So the edge connectivity in the graph H, in the solution, between S and T should be at least the demand. Okay. So this would be the variant, the edge connectivity SNDP problem. Okay. While if you would say, okay, the vertex connectivity, so you have kappa H ST, so this is the vertex connectivity, is at least the demand. Well, then you get the vertex connectivity SNDP problem. Okay, and now you want to minimize the costs of this graph, right? Meaning that you minimize the total edge weights of the graph that you pick as your solution. Yeah, and note that there are some special cases that you should recognize if you've ever read something about this topic. So, which is first of all okay, Steiner forests, or okay, let's start with Steiner tree. Oops, the Steiner tree problem is simply when dst equal 1 for all terminal pairs, right? And Steiner forests is also a well-studied special case, and here the demands are simply 0 or 1 for all st. Okay, and note that, I mean, if the demands are at most 1, it doesn't matter whether it's edge or vertex connectivity, right? It's the same. Yeah. Okay, so, well, of course we know, so okay, I mean, this SNDP problem is also well studied, but I mean, especially Steiner tree, but also Steiner forest is like very classical problems, so we know a lot. So that's kind of our starting point. So in particular, we know that the Steiner tree problem is NP-hard. And so SNDP is also NP-hard, right? No matter which variant you look at. Okay, so that's the first thing. It's NP-hard. Okay. Now, what do we do? Okay, so in combinatorial optimization, I guess there are two kind of main things that people do. One is approximation, and the other is parameterized algorithms. And let me first talk a little bit about approximation, because the thing is that this problem has been studied a lot in approximation for approximation algorithms. Okay, so if we want to do some sort of approximation, right? What does it mean? We compute a so-called alpha approximation for some alpha, which is some solution that costs at most alpha times more than the optimum solution that we're actually looking for in polynomial time, right? So we want to be very efficient with the running time here, but we sacrifice on the solution quality, right? Okay, so what is known? Okay, so for the edge connectivity version, there is a very seminal result by Jane. So Jane showed that you can get a 2 approximation algorithm. And this is a seminal result because so Jane introduced this thing called iterative rounding for this problem. And since then, you know, this method has been studied a lot, has been very influential for approximation algorithms and so on. Okay, at the same time, right, we also actually know that the Steiner tree problem is also APX hard, which means that like unless P equals NP, there is no approximation scheme, polynomial time approximation scheme, which means that you can, in such an algorithm, you would be able to set alpha to 1 plus epsilon for any epsilon, constant epsilon greater than 0. So you could come arbitrarily close to the optimum. Okay, so that's not possible, but you can get a 2 approximation. Okay. Now, in contrast to this, the vertex version, the vertex connectivity version, is a lot harder. So here, first of all, okay, so I'm gonna already introduce a couple of parameters. We're gonna study several parameters here. And one of them is the maximum demand. Okay, so let's say Dmax is just the maximum over all of these demands, right? And there are two hardness results here in terms of approximation. So the first one is if the maximum demand is somehow, let me write it formally, is polynomial. So polynomial in the input size, which I call n. So if the maximum demand is allowed to be very large, okay, then there is a lower bound that says, okay, there is no, what does it say? There is no 2 to the log 1 minus epsilon n approximation, unless something strange happens. Let me not write the conditions here. I'm not interested in that here. Yeah? Okay, so essentially kind of a log approximation would be the best you could hope for this SNDP, for the vertex connectivity SNDP problem. And then there's another one which says, okay, I mean, this is only when Dmax is very large. What if it's small? So you can also say if this is constant, okay, there is also a lower bound. And this one says that there is no Dmax to the epsilon approximation for some epsilon greater than 0. Okay, so somehow this maximum demand is a barrier for polynomial time approximations. Okay, so that's in terms of hardness, but then in terms of algorithms, there is there is an O of Dmax cubed times log k. So what is k? K is the number of terminals here, which is sort of a very typical parameter. That's what one can choose. And okay, so there is such an algorithm in polynomial time. So this is a result by Chuzo and Kana. And yeah, so this leads to another interesting concept, because actually, so to obtain this approximation algorithm, what they do is, so this is for vertex connectivity, right? But actually what they do is they use an algorithm which is similar to this, but for a problem that sits in between these two. Okay, and what is that variant? It's called element connectivity, SNDP. Okay, so for this, I will introduce the element connectivity. So, okay, so it's called element connectivity, which is like, it's called kappa prime. And then, okay, we're usually interested in this H, but okay, for some graph between S and T, right? So this so this is the maximum number of ST paths that are element disjoint. So element disjoint. And okay, what are the elements? So the elements are the edges and the non-terminals, which I also call Steiner vertices. Okay. So in other words, it's the maximum number of paths between S and T, such that no pair of them shares, or so that any pair of them can only share terminals. Okay, so they can only intersect on the terminals, but not on the edges and not on the non-terminals. Okay, does that make sense? Yeah. Okay. Good. And right. And now the thing is that for this, so and now okay. So if you do the same thing here. So if you say that, okay, now the element connectivity should be at least the demand, then you get the variant, which is element connectivity. I'll abbreviate it with LC, element connectivity SNDP. I hope you can read this. Okay. And the thing is that for element connectivity SNDP, we have two approximation, which I think is given by Fleischer et al. Fleischer et al. And it's essentially, it's a generalization of James' algorithm. So it also uses iterative rounding. And the thing is, using this algorithm, actually, this algorithm is constructed. Okay, I won't go into the details. But in any case, so while edge connectivity and vertex connectivity are kind of sorry, here these two are kind of very natural variants because we know what edge connectivity and vertex connectivity are. There is also this kind of in-between thing, which is element connectivity, and it's important. Well, has also been studied a lot because of connections to the other things. Okay? Right. Okay, so this is in terms of approximations. Now let's talk about parameterizations. Right, so now we're interested in like FPT algorithms, okay? And well, I'm sure you all know what it means, but still, right? So now, instead of sacrificing on the solution quality, we sacrifice on the running time, right? So we want to compute the optimum solution, but we are also given some sort of parameter, which is some integer, and we are allowed a running time that is any function in the parameter, which I call p, times some polynomial in the input, right? So for parameter p, whatever this parameter is, right? Could now describe a lot of different things. So what do we know about parameterization? So that's the thing. We don't know too much about SNDP. There are some results. I will mention kind of the most classic one here, which again, if you know something about standard tree, you know this, but this is this Dreyfus-Wagner algorithm. Dreyfus-Wagner. So they show that for Steiner tree, you can compute an optimum solution in time 3 to the k n to the O of 1, right? Where k was the number of terminals. Okay, and I mean, there are some maybe better algorithms, faster algorithms than this, but let's not talk about that here. Okay, so, but we will need this, the fact that this standard tree is FPT for number of terminals, we will use again. All right, so what we do, right, is we look at these problems, and again, so for in terms of approximation, what we see is that we have edge connectivity and element connectivity, and for both of them, we have fairly good approximation ratios, while the other version, the vertex connectivity, well, we have this approximation, but we also know that there is no constant approximation, so it's much harder. And in some sense, we show that we can, I mean, we get a similar picture in terms of parameterization. And the parameterization we are interested in is the solution size, which is kind of a typical parameter that is studied for a lot of problems, a very natural parameter. So, okay, if we look at edge connectivity SNDP or element connectivity SNDP, okay, then these can be solved in some running time of 2 to the O of L times n to the O of 1, where L is the solution size. Okay, so the number of, let's say, number of edges and vertices in this graph H that minimizes the cost. Okay, that's one thing. But then we also show that for vertex connectivity, again, the problem is much harder because there's under, again, complexity assumptions, there is no such algorithm. And before I write down that result, we can actually we can look at some special cases and show that it's true even there. And let's see. So we have the, first of all, if we look at single source, let me put it here because there are actually some approximation algorithms here also. So single source variant would mean that somehow there is this special terminal called the root, and the demands are only between the terminals and the root, okay, and nowhere else. So yeah, it's kind of like Steiner tree. You can think that one of the terminals is the root. You want to connect to the root, but now you just have demands. Okay, so it means there somehow exists this special terminal, and like if the demand between the root and the terminal is like can be non-negative, but if you look at any ST, then this is 0 if S and T are not the root. Yeah? That's one thing. And then there is the uniform case. Uniform. So this just means that all the demands are the same. Okay, so this means dst equal to some given d for all terminals. And okay, so if you look at single source vertex connectivity SNDP, okay, you can get something better than this because you can actually get an O of d max squared approximation. And if you look at okay, so if you look at the uniform single source solution, so if you have both uniform and single source, then you can get an O of d log d approximation, right? Well, d is this common demand between all of them for vertex connectivity SNDP. And okay, so we will also look at uniform single source version. That's one thing, but also we will also restrict the number of terminals. And so note that, you know, if the number of terminals is 2 only, then you can just solve it using some flow algorithm. It's simple, right? So that's polynomial time. But we show that increasing the number of terminals by only 1 makes it hard. Okay, so here's the theorem that we get. So the corresponding hardness results is if you look at uniform single source vertex connectivity SNDP. So this is W1 hard, okay, whatever that means. It means, I mean, in particular, unless something strange happens, there is no FPT algorithm that has this kind of running time for the parameter solution size, which is called L, right? Even if the number of terminals is 3. Okay. All right. How much time do I actually have?
20 minutes.
Okay. Good. So in that case, so there are some more results, but let's skip those results. Okay. And because let's talk about this. I want to tell you a little bit about the techniques here. Okay. So let's talk about this theorem and how to prove it. All right. So yeah, the main ingredient is actually something that was known before, which is something called the reduction lemma. And okay, so first thing I should say, okay, what we actually show is that this problem, the more general one, is FPT, and it's easy to reduce this one to this one, the edge connectivity to element connectivity. So how do we do this? Okay, so So there's a simple reduction from element connectivity, sorry, from edge connectivity to element connectivity. So if we have a non-terminal, a Steiner vertex, in this instance here, okay, with some edges connected to it, what we simply do is we replace it by a clique of size degree of that original vertex. And then for each vertex in here, we just connect the previous edges to these, so that every edge connects to exactly one of these vertices. Okay, and then we give the edges in the new edges that we introduced. They all have weights 0, right? And the original edges, they have some weights. Let's call it W. You just keep the same weights. And then it's kind of easy to see that, well, if you have a graph which has a certain edge connectivity, like a subgraph of the original, right? And then several paths might go through this this vertex. Well, now you can route them so that you don't use the same non-terminals in the solution. So it becomes element disjoint. Okay, and the cost is the same because these additional edges that we use are cost 0. Okay? And you can also go in the other direction. Anything that has like certain element connectivity here, you can just contract the edges and you get something that has edge connectivity. So that's easy reduction. So let's concentrate on the element connectivity version. Right, and for this, we have this lemma, and this is something that was proved by Chicory and Corolla. So Chicory, Corolla. So they call it the reduction lemma, but okay, whatever. So it says like that we're given an arbitrary graph. We're given some terminals. And now let's pick an edge which connects two non-terminals. Okay, so meaning that if we intersect E with the terminals, right, it's the empty set. Okay. Now let's define G1. G1 is the graph that you get by deleting the edge. And G2 is the graph that you get by contracting the edge. Or it should be, yes, no, like this. Yeah. You contract the edge, and let's remove loops and multiple parallel edges and these things. Then at least one of the following is true. So the first case is that actually between any two terminals, the element connectivity is maintained in G1. So that means the element connectivity in G1 between any two terminals is the same as before. Well, or it happens in G2. Okay, so for all terminals, we have that the element connectivity in G2 between these terminals is the same as the element connectivity in G between the two guys. Okay, it's not very hard to prove, but okay, let's skip that because anyway, it's a known result. Okay, but let's try to use this. So one observation that you can make is if you, and this was also made by Chicory and Corolla, is that okay, if you look at the graph and first of all, okay, if you have two terminals that are connected by an edge, you can just subdivide the edge and put like a non-terminal in between. That doesn't change anything. And okay, you pick weights for those edges accordingly. I mean, let's just give them half of the original weight or something. So that means that without loss of generality, we can assume that the terminals form an independent set, right? Okay, so we have the terminal set, which is some sort of independent set. And now if you apply this lemma repeatedly, So you get rid of all of the edges between non-terminals, right? Then in the end, the non-terminals also form an independent set, right? So then you have V without R, and so you get a bipartite graph actually between the terminals and non-terminals after applying this lemma exhaustively. And this is essentially what we're going to exploit. Okay, and let me put sort of the main lemma here that we prove. So it's a structural result which describes the solution to to this element connectivity problem. So let's say I have H, and this is a minimal solution for element connectivity SNDP, right? So minimal means that I cannot remove any of the edges from H without making the solution infeasible. So for example, let's think about an optimum solution. That's a special case, and anyway, what we're interested in. But minimality is actually enough here. Okay, so then there exists these trees. Okay, they're called T1 up to TB. All of them are part of H. And okay, the first thing is that if you take the union of all of these trees, you have the graph. So they kind of cover this the solution, right? Like this, okay. And also, if you look at the intersection of two such trees, so if you take if you take the vertex set of Ti and intersect it with the vertex set of Tj, then this is always these are only terminals. Okay, so they only intersect in terminals. And furthermore, the leaves of every such tree are from R, are also terminals. So what this means is, if you look at the solution, then okay, so you have these terminals somewhere, and they have a certain connectivity, right? But the thing is, you can now take the solution and you get like these trees that connect these these terminals, right? So somehow they look I don't know, something like this maybe. Let's say like this, yeah. So this is what a solution looks like. Okay, and there's something more, which is a little bit more of a technical condition here, but you can actually also say that if you now I have to find two guys. So let's say between maybe this guy and this guy, right? You have two of these paths like this, yeah. And you can say that let's fix for any terminal pair. Let's just fix the maximum number of element disjoint paths. Then every one of these trees contains at most one of these paths. Okay, so you can make sure that you don't have a tree where like two of these paths go through. Okay, so what it says is so for every terminal pair there exists DST like element disjoint paths such that, see if I can squeeze it in here, such that any TI like intersects at most one of them. Okay. Right now, before we try to prove this, let's just see from this, this FPT algorithm easily follows, because you can just use color coding. And okay, do you all know what color coding is? Who does not know what color coding is? Okay, so if everyone knows what color coding is, then it's going to be very quick to explain. So what you simply do is, yeah, you essentially, for every terminal and every standard vertex, you will guess in which of these trees to which of these trees they belong, and that's essentially it. Because then you can just use this Dreyfus-Wagner algorithm to compute each of the trees separately, and that's your algorithm. Okay, so to make it a little bit more explicit, maybe. So for so for non-terminals, okay, we will color them with B colors. So B being the number of these trees, right? Here. And for terminals, we will color them with sets of these colors, so 2 to the B colors, right? Because the terminals, they can be in several trees, so we will just color them so that each terminal has now a set of colors, like C from the set of colors, which encodes in which trees it's gonna be. Okay, and then right, and now because you have colored everything. Oh, and then okay, so then you take right. So now you from this you color the edges. Okay, so you will color an edge with color B if like the two vertices connecting. I mean, yeah, connecting it both have color B. Right, and then you keep only those edges that have a unique color, and then you have a graph. Or you can see it this way. Okay, you just take the graph induced by a color. Okay, so you look at like GI, which is the graph induced by the vertices that have a color I, which for terminals they might have several colors, but at least one of them is I, right? And then you just solve Steiner tree, yeah, on this graph. Okay, and that gives you an FPT algorithm. And okay, and this is parameterized by the solution size, right? Because we have to color the whole solution. Yeah? I mean this algorithm is parameterized by number of terminals, okay? But okay, number of terminals is upper bounded by solution size. That's fine. But in the end, yeah, the total parameter is the solution size, because you have to like make sure that every edge in the solution or every vertex in the solution has the correct color. Yeah, so that's your parameter. All right, so let me try to sketch. Are there any questions to this, or I think it's pretty straightforward? It's simple, right? Okay. So let me try to sketch the proof of this lemma. So what do we do? Actually, how do we start? Let's see. Okay, right. So the first observation is, so let's start, you know, we take this minimal solution H and we apply this reduction lemma. Where is it? The upper one, right? And let's say And let's say, okay, we take a sequence of these applications. So we start with H, then we take H1, and so on. And in the end, we have some H, I don't know what I call this, some H something. HH, okay, very great name. Okay. So this is a sequence of graphs that we get by applying the reduction lemma. Okay. And the observation is that, well, actually what happens, because you don't know whether you're gonna delete or contract an edge in each step. But actually what happens is that you will never delete an edge. You will only contract edges. Okay. Why is that? Well, in the first step, this is clear because this is a minimal solution. By definition, it means you cannot delete an edge, right? Okay, but once this is true, then by induction, you cannot delete another edge, right? So if you had an edge that in some edge I, and imagine you could delete it, right? Well, then you could go back to hi -1, and I mean there's some operation that went from here to here, right? But no matter whether it was okay by it should. By the induction hypothesis says this hi was produced from this by contracting an edge. And okay, but now if you look at any terminal pair and you look at all of the in this graph and all of the you know that there are still enough element disjoint paths that somehow connect these two things, right? But that means that you could have actually deleted this edge already here, which is not true by the induction. Okay, so it means that we only use contractions. And now again, let's apply this lemma until we have a bipartite graph. Exactly. So let's apply it until, so in H is some bipartite graph, right? And so we have the terminals on one side and we have the non-terminals on the other side. And okay, so now we have like stars, right? So the solution currently is a bunch of stars, which may intersect on the terminals. So it looks something like this. Okay, and now what we do is let's call these stars S1 up to SB. Okay, so we have B vertices here, and now let's just go all the way back to H by uncontracting edges. Okay, that means that every vertex here just gets blown up into some graph, and I claim that each such that there will not be any cycle actually in this graph, right? So we took the star, it looked something like this, right? And we uncontracted, so that means we have these terminals, and okay, there is some sort of graph here that connects them. And let's say there is some sort of a cycle in this graph here. Right. Okay, so I skipped one thing. So remember, there's this other condition here, which says that you can fix this disjoint path such that any tree intersects with at most one of them. So let's do that already here in this thing, right? We know that between S and T, somehow there are enough element disjoint paths. And well, here it's easy to see that this condition is true, right? Because these paths, they're element disjoints, and well, they are. I mean, otherwise they would somehow use this vertex into two of these paths, right? So you get this nice condition. And okay, so now if you look at any terminal pair, it doesn't have to be these ones, but in this graph, and you know that in the star there was somehow this path. I mean, yeah, here, right? Which maybe went through here, but only one of these paths, right? And that means that here, if you, let's say I take an arbitrary edge of this cycle and just delete it. well, then I can still route this path, some path through here. And because there is no other path going through this thing, right, I cannot make any mistake here. And that means that actually this thing is a tree, which is what I needed. And also I get this condition about the paths. Right? And okay, I didn't show you why I needed this condition on the paths, but I mean, you need it somewhere also for this algorithm to work. But I mean, okay. Is that about the time I have, or yeah? Because then let's just stop here.
Okay, thank you. So, questions? All right.
It's all very simple, right? So, actually, I mean, so you have some other results, and it's like, so this hardness result is maybe the only one that is not like very simple. It's still simple, but you have to use, because it's not a standard straightforward reduction. You have to use some trickery. But here it's kind of, you know, once you have this reduction lemma, then this follows, and the algorithm is simple, and so all the other results are also like that.
What was the hardness reduction? It's from which problem?
Yeah, so here we use grid tiling. If you know this. So a standard reduction would be like multicolored clique, right? The problem is that if it's undirected, so we also have a hardness result for directed graphs. And they're like multicolored clique. It's very straightforward. But for directed graphs, you can control where the paths go very easily. For undirected graphs, it's tough because, I don't know, the paths go like everywhere. It's crazy. But if you have sort of a grid structure, then you have like a lot of these paths and they sort of block each other. And you can do something like
that. I have one unrelated question. So you seem to be now an expert in this Steiner things and Survivable Network.
Yes.
Is there anything known about kernelization except for this standard that Steiner tree doesn't have a kernel and maybe some kind of kernel in Parametrized?
I mean, yeah, I mean, the short answer you already gave, right? So, I mean, of course, these are all generalizations, so somehow I'm not sure what to expect there. There is, however, I mean, it's a bit of a different setting, but it's kind of related still. If you think now, so I mean, so in the directed setting, so if you take Steiner forests and just take the directed version of that, so directed Steiner network is called, right? And then if the graph is planar and bidirected, you can get a polynomial like what is it called now? A PSAX, like a polynomial size kernelization approximation thing. Whatever this acronym stands for again, right? And then Dushan, I mean, in our paper we had also for Steiner tree. So let's think. So if you parameterize by the number of Steiner vertices, right? You can also get an approximation scheme kernel in that case.
And what is in the solution?
For the Steiner vertices in the solution, yes. So I'm not sure what exactly if you have something in mind, or because yeah.
Okay, so are there any further questions? If no, then let's thanks again.